Welcome back everyone. In this lecture I will actually tell you how to construct this quotient algebras from the ideals. Okay, let us start. Let us fix this Lie algebra G. Lie algebra over complex numbers. Okay. So, before actually getting into the definition of ideals, so I would like to first motivate the notion of ideals from the homomorphisms. Okay, that is a natural way to actually get ideals. So, if I have a map, let us say linear map which is also Lie homomorphism from G to G dash. Okay, let us say phi is actually a Lie homomorphism. So, then what we do, we look at what is called the kernel of this map. Okay. So, the kernel of this map makes sense as a linear map. So, what is this kernel? So, this is called kernel of the map phi. So, this is those elements in G such that, so those are mapped to 0 via this map phi. Okay. So, this is indeed a subspace of this G. Okay. So, now let us see what happens if we assume this phi is Lie homomorphism and whether we can get any extra property about this kernel. Okay. First of all, one can ask whether this kernel is actually a subalgebra or not. So, let us see whether it is a subalgebra. So, let us start with two elements from this kernel. So, let x, y from this kernel phi. So, then what we want to see whether the bracket of x y, whether it is in kernel of phi or not. So, then let us compute what is the bracket of x y under this map. So, then since this phi is actually a Lie algebra homomorphism, you can see that this is nothing but phi of x, phi of y, bracket of that. So, then since phi of x, phi of y both are 0. So, this implies this map phi of bracket x y is 0. Okay. That implies the bracket x y is indeed inside the kernel of phi. So, that is what we wanted to show. So, now more than this, actually you can see from this equation, if one of this phi of x or phi of y is 0, so then the bracket is going to be 0. So, that means you can assume this x is coming from the Lie algebra G and y is coming from kernel phi, but still we will have the bracket x y is in kernel phi. Okay. What I am saying, suppose if x is in G and y is in kernel phi, then still we get the bracket of x y is 0 under the map phi. Phi of bracket x y is 0. So, what does it mean? That means we still have this bracket x y is in the kernel. Okay. So, this property is actually very important property. So, this actually kind of duplicates the property that you have seen in the ring theory, where the product is just assumed to be associative product. Okay. But here the product is general product, but still this thing holds. Okay. The product between x and y is in this kernel phi for all x in G and y is in kernel phi. If this property is what very important property for the kernel. Okay. So, we will isolate this property and we call a subspace satisfying this property as an ideal. Okay. So, what is the definition of ideal? So, you start with a subspace. Okay. A subspace I of G is said to be ideal if the following holds. Okay. What holds? So, whenever you take x from G and y from I, So, then the bracket of this x y should be in I. Okay. So, that is the property. If a subspace satisfies this property, then we call this is an ideal. It is immediate that ideals are subalgebras. Okay. So, it is easy to see ideals must be subalgebras. Okay. We also seen from the previous discussion, kernel of any Lie homomorphism is an ideal. Okay. So, indeed we will see that any ideal will be actually arising as kernel of some Lie homomorphism. So, for that we need to actually introduce what is called this quotient algebra, which is actually a new way of getting Lie algebras from existing Lie algebras. Okay. It is a procedure to get more interesting classes of Lie algebras from already known Lie algebras. So, we will do that in a minute, but before that I would like to give some examples of these ideals, okay, and we will also see some elementary properties of these ideals. Okay. So, let us see some examples. So, if we actually take this abelian Lie algebra, let us say G is abelian Lie algebra. So, then any subspace will be actually ideal inside abelian Lie algebra. So, then any subspace I of G is an ideal of G. Okay. That is easy to see because all the Lie products are trivial. Okay. So, that says any subspace becomes ideal. So, now let us take our favorite example, for example, general linear Lie algebra. So, GLN of C. So, then I would say like now consider this SL and C sitting inside GL and C. So, then it is easy to see this SL and C is an ideal inside GL and C. Okay. So, SL and C is an ideal of GL and C. So, why this is true? Suppose if you start with some matrix A in GL and C and then some matrix B in SL and C. So, then what will happen to the commutator? The commutator is nothing but AB minus BA. Now, if you compute the trace for the commutator, then that will be the trace of AB minus BA, which will be 0. Okay. So, that implies for any A in GL and C, B in SL and C, the bracket AB always lies inside SL and C. Okay. So, that means the property star is satisfied. So, SL and C is an ideal. So, before actually moving forward, I want to give you a warning. So, in general ring theory, we talk about left ideal and right ideal, because we will not assume anything like commutativity about the product. Okay. But even though we do not have commutativity here in the Lie product, still we do not care about this left and right ideals, because left ideals will become right ideals and they also become two sided ideals using skew symmetric. So, since we have this skew symmetric, bracket x y is same as bracket y x. So, that implies left ideals are same as right ideals and that same as two sided ideals. So, we do not distinguish between this left, right or two sided ideals. Okay. We will only talk about ideals in Lie theory. So, now let us move on. Okay. So, now what we want to do, okay, given ideals, we will see how to make some new ideals out of it. Okay. Let us say I and J are two ideals of G. So, then immediately what one can do, one can actually talk about the intersection of I and j. Okay. So, this is those elements in G such that x is in I as well as x is in j. So, it is easy to see that the intersection of these two ideals must be again ideal. Okay. So, this is again an ideal in G. So, it is easy to see that intersection of subspaces is again a subspace. So, now what we need to prove, suppose if x is in G and y is in the intersection, then we need to prove that the bracket x y should be in the intersection. Okay, but that is obvious because once we have x is in G and y is in I intersection j. So, that will imply the bracket x y will be in I by using the definition of ideal for I, and that same argument will tell you bracket x y is in j. So, that will imply that x bracket y that is actually inside I intersection j. Okay. So, this says that I intersection j must be an ideal for any ideals I and j, and this is not only true for only two ideals. So, these arguments will hold for any intersection of like any family of ideals. Okay. So, that I will leave it as exercise. So, now given these two ideals, we can also make one new space called the sum of these two ideals. Okay. So, what we can do, given these two subspaces I and j, we can talk about I plus j, which is the sum of these two spaces. By definition, you add all possible elements from I and j. So, then it is easy to see that I plus j is again a subspace of G. So, now we claim that it is indeed ideal. So, I plus j is an ideal of G. Okay. So, that is again like not very difficult to see. So, what we need to prove? So, we start with some x in G and then some y in I plus j. Okay. So, then we need to prove that the bracket x y is in actually I plus j. But note that since this y is in inside I plus j. So, the y is of the form some z 1 plus z 2 for some z 1 is in I and then z 2 is in j. So, now if you take the bracket with x, then what will happen? This will actually split into x z 1 plus x z 2. But note that x is in G and z 1 is in I. So, this is in G, this is in I. So, that means the bracket will be in I. For similar reason, this x is in G and then this z is 2 is in J. So, that implies that this bracket is in J. So, that implies this bracket x y, which is sum of two elements, first one is in I and the second elements in J. So, then this will lie inside I plus j. So, that proves that the bracket of this x y is in I plus j. So, that means I plus j is an ideal. So, just to use some shorthand notation, whenever I say I is an ideal in G, I just use this triangle to denote this. Okay. So, this means I is an ideal of G. Okay. So, now here is one interesting actually construction. So, this is called product of ideal. Okay. So, this I plus j, so this is called the sum of ideals. Okay. So, now we can talk about what is called product of ideals. So, what is this? So, you just denote this by bracket I j. So, what is this bracket I j? You take it to be the span of all this bracket x y, where x is coming from I and y is coming from j. Okay. So, now what we claim? We claim that, so this is again is an ideal. So, this is ideal inside G. Okay. So, here we need to be little bit careful, because the typical element in bracket I j will be combination of all these products x y. Okay. So, in particularly if we take x in G and some y in this bracket I j, so then we can write this y as sum of some x I e z I, okay, where I range from 1 to n, and where this all these x i's they come from this capital I and all these z i's they come from capital J. Okay. So, now what we need to prove? We need to compute the bracket x y. So, let us compute and then see what happens. The bracket x y is nothing but summation I range from 1 to n bracket x bracket x I e z I. Okay. But now you can see that this is nothing but summation I range from 1 to n using the Jacobi identity. This is bracket x x I e z I plus bracket x I x z I. Okay. So, now look at this element, since this x I is in capital I, this x is in G. So, this bracket will lie inside I, okay, and then this is inside J. Similarly, this lies inside J and then this lies inside I. So, again this is commutator of two elements coming from, like one from I, another one from J. Similarly, here commutator of one element coming from I, another element coming from J. So, this is of this form. So, again, so this bracket x y is written as combination of elements of the form bracket x y, where x is coming from I and y is coming from J. So, that implies this bracket x y is in the bracket I comma j. Okay. So, this proves that this bracket x I comma j is an actually ideal. So, now I want to give you a slight warning. Okay. So, the warning is we need to have the span of bracket x y. Okay. So, we can't avoid this span in the definition of the product bracket I j. What is the meaning of that? So, I can't simply define the bracket of I j to be just the set bracket x y, where x in coming from I and y coming from j. That actually will not be ideal again. Okay. So, I can't give you an example right now. I will add that in the problem sheet. Okay. So, one has to actually work over real numbers to get such examples. But anyway, there is a very interesting question that actually pops up from this observation. So, I will actually, so I will just write down what I said. So, we cannot define bracket I j to be just bracket x y, x coming from I and y coming from j. Okay. So, this is actually wrong. So, you should think about it, and actually there are counter examples where this thing, this set even will not even become ideal. Okay. So, now here is the interesting question. Actually, once you actually think about writing something in terms of this brackets, okay, So, since this discussion came here, I am just writing this question here. So, here is the question. The question is, so we have defined a bracket, Lie bracket on G. Okay. So, one can actually ask this question for even subspaces or subalgebras or ideals and so on. But let us ask this question even for Lie algebra itself. So, you have this Lie bracket from G cross G to G. Okay. So, now the question is, so what this map does? This map does given x y, it maps to bracket x y. Okay, that is all it does. And this is a bilinear map, and this is actually Lie bracket. So, now what is the question? The question is, when this map is surjective. Okay. So, that is very legitimate question, or can you like specify some classes of Lie algebras? One can ask whether this map is surjective or not for that classes of Lie algebras, and lots of research is actually done in that direction. Okay. As an example, I will just give you one exercise. Okay. So, that exercise is actually going to answer this for SLNC. Suppose if you take SLNC, so then the answer to this question is affirmative. That means, so I will write in very detailly. Okay, given any matrix Z inside G, so that is means it is just a traceless matrix. Okay. So, then there exist some x and y again inside SLNC such that this Z can be written as bracket x y. Okay. So, this is not that easy fact that one expects. Okay. But this can be proved, and I will leave it as exercise for you to think about it. This is very interesting exercise. Okay. And that means any element in SLNC is actually simple commutator, that is what it says. Okay. So, these kind of Lie products, you can call it like simple products or simple Lie products or simple commutators. So, each element of SLNC can be written. So, this is actually true even for any element of like JLNC. So, that is not hard to see. Again, you take traceless matrix. So, to get this condition, you need to start with traceless matrix, because trace of any commutator bracket x y must be 0. Okay. So, basically what it says, this exercise can be rephrased as follows. Suppose A is a matrix, then A is actually traceless if and only if A can be written as B C for some B C coming from M of C. Actually, here I am doing something more. Okay. So, this is we are demanding x and y to be traceless again. Okay. In this first question, but in the part B we are not demanding that. Okay. So, it is actually somewhat simpler version, but still you will be able to do this. Okay. Because A is harder than B. Okay. So, this is just aside, I just wanted to give you this small exercise. So, now let us go back to what we have been doing. Okay. I defined the product between two ideals. So, now what we can do, we can also talk about a product of this G itself. Okay. So, I and J we can take it to be G, then we can talk about the product of that. Okay. So, what it is actually? So, that in that special case we call this as the derived algebra. Okay. So, this is called the derived algebra, and it is easy to see, because from our earlier proof this derived algebra is an ideal inside G. Okay. And here is a small observation, is G is abelian if and only if this derived algebra is just 0. Okay. So, this is largest subspace. In some sense, this derived algebra is actually does the role of this commutator subgroup of some commutator subgroup of a group. Okay. That is the role it exactly does. So, here is one exercise. So, now once we have defined the notion of derived algebra, then one can ask, okay, derived algebra of various known Lie algebras. For example, compute, okay. So, compute the derived algebras of G, where G is GL and C, SL and C, and like B and C and N and C. Okay. So, these are all the examples that we have seen. So, you can actually try to compute. For example, it is not hard to prove, okay, when you take the derived algebra of SL and C, then you get back SL and C. So, this is something you can verify. Okay. Maybe I will do it during the problem solving session. Okay. This is all about product of ideals and sum of ideals and so on. So, these are all the ways one can actually get some new ideals. Now, given these ideals, we want to actually construct some new Lie algebras, okay, called quotient algebras. So, these quotient algebras is actually a procedure to get new Lie algebras from old Lie algebras, and then let us see how one actually gets that. So, all of you must know what is quotient space from first course in Lie algebra, linear algebras. Okay. So, that I am not going to actually really recall, but anyway I will tell you what is the quotient space definition, and then we can go from that. So, how do I construct this quotient algebra? Okay. So, you start with the Lie algebra as before. Okay. Let G be a Lie algebra over complex numbers, and then let us say I is an ideal inside G. Okay. Then one can, because it is a subspace, one can immediately talk about what is called this quotient space. So, this is just a quotient space. So, what is this quotient space? By definition, you take all these cosets corresponding to this subspace I. Okay. Basically, you define a equivalence relation. Okay. You define an equivalence relation on G with respect to this subspace I, and then you take all possible equivalence classes with respect to that equivalence relation. Then you get these classes as these following cosets, which are all nothing but translation of this I. Okay. I will just write down all these cosets. I am not going to recall what this equivalence relation and so on, but it is obvious that once I give you these cosets, then it is also like equivalent to giving the equivalence relation. So, what are all these cosets? These are all nothing but the translation of all this translation of this capital I, where it is coming from G. Okay. So, you must have seen in elementary linear algebra, this is actually a vector space again over complex numbers. How the addition is defined? So, you can actually add two cosets by adding some representatives. You call Z1 is representative, Z2 is representative from the second coset, then you just add it by adding them and then taking the corresponding coset. And it is easy to see, this is actually a well defined addition on G modulo I. Similar to that, you also have scalar multiplication. Suppose alpha coming from complex numbers, and then this Z plus I is an element of G mod I. Then what is the product alpha Z plus I? So, this is the scalar product which is defined to be alpha z plus I. Okay. We use the scalar product, the scalar multiplication and the addition that are already available in the ambient space to define addition and scalar product for this quotient space. Okay. And I will leave it to you to check both of these are well defined operation on G modulo I, and then with respect to this addition and scalar multiplication, this G modulo I becomes vector space over complex numbers. Okay. So, G mod I is a vector space over complex numbers. So, that is something we know already. So, now what we want to do, we just want to define leap product on G mod I. We already have a leap product on G. So, we will be using that leap product. Okay. So, you take two elements and then just to define its leap product to be. So, you use the leap product that you have already in G and then take the corresponding coset. Okay. So, this is the natural definition that one expects. So, you just use that to define this. Okay. Now, here is the question. The question is whether this product is well defined or not. Okay. Even when you do this ring theory and all, when you start with two sided ideal and go modulo that, and then you will be able to define product there, you have this question whether that is an again well defined product or not. Similar to that, we ask this question here. So, let us verify this is indeed well defined product. For that, okay, we just choose two different representatives and then see whether what you get. Okay. Suppose x plus I is equal to x dash plus I and y plus I is equal to y dash plus I. That means these two cosets are equal. So, we have two different representatives for first coset, and for the second coset again we have two different representatives. So, then we just want to say if I take this bracket x y plus I, that should be same as the bracket x dash y dash plus I. So, which is equivalent to saying that, okay, this is equivalent to saying that the bracket x y minus the bracket x dash y dash, that should be in I. Okay. So, it is you know already by definition x plus I equal to x dash plus I if and only if x minus x dash will be in I. Okay. This is the definition of two cosets being equal. Okay. So, because of that we need to verify whether this is true or not. Okay. This is the what we need to verify. So, let us verify whether this is true, and then if we verify, then this gives you well defined leap product. Okay. So, let us do the calculation. We already know that x minus x dash is in I. Similarly, y minus y dash in I. So, now what we need to prove? We need to prove that the bracket x y minus x dash y dash is in I. Okay. Let us do this computation. You compute bracket x y. Now, what we can do? We can just add and subtract x dash, and then here again you can add and subtract y dash. Okay. So, if you do that, then if you just use this linearity, then what do you get? You get bracket x minus x dash comma y minus y dash plus y dash, okay, plus x dash. Okay, I do not use this comma, maybe I will erase. So, this is x dash y minus y dash plus y dash. So, note that this x minus x dash is in I. Okay. So, that means this element, this is in I. Okay. So, now if you take this second element, what's happening, because we want to do it modulo I na. So, this is some element, let me call this is xi. So, this is xi plus x dash, sorry, x dash y minus y dash plus x dash y dash. Okay. So, you can see that since this y dash is in I, this entire element is in I. Okay. So, that means, so this is some psi dash, so that is also in I. So, this is you wrote it as bracket x y equal to psi plus xi dash plus x dash y dash. Both xi dash both are in I. So, that will imply xi plus xi dash is in I. So, that means this bracket x y minus x dash y dash. So, this is in I. Okay. So, that proves that the bracket that we defined is actually well defined. Okay. So, that means the bracket is well defined. Now, I just leave it to you to check this bracket is indeed gives you bilinear map, because this is induced from the bilinear map, this has to be bilinear. So, that is the reason, and then since it satisfies skew symmetric and the original bracket, that is actually satisfying skew symmetric and Jacobi identity. So, this induced bracket will also satisfy skew symmetric and Jacobi identity. Okay. For example, if you want to just define if you want to just check skew symmetric, here is the proof. So, you take x plus I and then x plus I. So, then the bracket will be bracket x x plus I, which is 0. So, you get 0, okay, 0 plus I, which is 0 inside G modulo I. So, similarly, I will leave it to you, check Jacobi identity satisfied by this product. Okay. So, that makes now this as Lie algebra. Okay. You have this G mod I with this new product, okay, which is induced from G. So, that makes it Lie algebra. Okay. So, this is one way to actually get some interesting Lie algebra. So, you can actually, like, as an example, let us see, we already have some homomorphism from earlier lectures. We will just see what will be the quotient using that, okay. Because the kernel of that homomorphism will be ideal. So, that actually kind of tells us somewhat how to handle the quotient. So, that is all, like kind of we can get information about this quotient algebra using what is called isomorphism theorems. I will actually prove prove those isomorphism theorem in the next lecture, okay. But before that, let us just see like some basic properties of this quotient algebras, okay. So, there is this natural map, okay, from this G to G modulo I. So, which is called the quotient map, okay. What is this map? Let me call it pi. So, this takes x to x plus I. So, this is a natural linear map, C linear map from G to G modulo I. So, this map is actually it is easy to check, it is C linear, okay, because this G modulo I is quotient space. This is indeed actually Lie homomorphism. So, that also one can check. So, because that is obvious from the bracket, okay. So, what does it mean by it is a Lie homomorphism? You take bracket of x y and then look at the image of that, then that should be bracket of pi of x, pi of y, okay. But what is pi of x y? Pi of x y is nothing but bracket x y plus I. So, but that is by definition is x plus I comma y plus I. So, which is nothing but bracket pi x pi y, okay. So, that way you verify that this quotient map, which is the natural map, okay, this is called quotient map, is actually naturally a Lie homomorphism. Then what will be the kernel of this map? So, it is not hard to see, the kernel of this map will be just I, okay. So, that is not very hard, because what is the kernel by definition? The kernel by definition those x in G such that when you look at pi of x that should be 0, but what is that? By definition this is those x in G such that x plus I should be 0, but x plus I should be 0 is same as x plus I should be I. So, that means this is those x in G such that x is in I, okay. That is why this is I. So, the kernel pi is nothing but I. So, now look at some more informations. If I start with some ideal that contains I. So, let us say J is an ideal of G that also contains I. So, then what happens? I becomes I assume I is also ideal. So, let me rewrite. So, I is ideal inside G. Let us say I contains in J, J is also ideal in G. So, now you can ask this question, what will happen to the image of this J. So, you have this quotient map from G to G modulo I. So, then what is the image? So, the image is nothing but all possible x plus I such that x is coming from J. So, in shorthand notation one can just write this as J modulo I. So, there is no harm in that. But now the question is, since J is an ideal inside G, can we say something more about this J? So, actually one can claim this J mod I must be an ideal. So, what is the claim? The claim is J modulo I is an ideal inside G modulo I. So, how one verify this? You start with some element x plus I inside G modulo I and then y plus I inside J modulo I. So, then you look at the bracket x plus I y plus I. So, then what happens? This will give you x y plus I. But what we need to prove? We need to prove this x bracket x y plus I should be in J mod I. But the thing is x is coming from G and y is coming from J, because y plus I will be equal to y plus I will be equal to y dash plus I, for some y dash is coming from J. So, that will say this y minus y dash should be inside I, which is subset of J. So, that will imply y is in J. So, that means I can assume this y is coming from J. So, because x is in G, y is in J. So, that already implies bracket x y is in J, because J is an ideal. So, that means if I take bracket x y plus I, so that is inside J mod I. So, that verifies that this entire term is inside J mod I. So, that means this is an ideal inside J mod I. So, this is actually a very important observation. So, these observations will be used later. So, actually I will continue with this isomorphism theorems later in the next class. So, right now I will stop. Thanks.